So hi, folks. Hi. So I felt the least I could do is apologize with Candy after continuing to mess up the description of the slopes. So you're learning why I carefully prepare handouts so that I can check that everything is right, and I try not to do things live because when I do, I invariably screw it up. And I figured out the hard way after class when several of you emailed me with the exact same pattern of error that I apparently induced in making your slopes. So let me clarify once and for all correctly what the code would look like to accomplish this coding scheme. So I know where the problem came in. It came in looping two things together. So state a code, what I had here saved from last time is fine. So I'm replacing, if experience is less than 4, is this chunk right here. So this part, experience minus 1, gets you here. Less than 4, actually just for the first 3. And the other one, 4 to 7, is 0. So that's cool. So that gets you the values from 1 to 3. The other one is greater than or equal to 4. Then we want to replace the top ones with 3s. That's what the the third line here does. And then replace this part right here with experience minus 4. So this part was okay. It was the SAS part that I screwed up. So in SAS, when you use these sorts of conditional logic, LT stands for less than. Can you guess how you would say greater than? GT. And then if you throw an E on there, it's greater than or equal to. And LE would be less than or equal to. So in this case, we're setting up the same two things can happen in one row if you have a do. These two things can happen in one row if you have a do. What I ended up doing is switching the order where I took these two and then these two, and that's where it got screwed up. So let me correct this once and for all. If experience is less than 4, so mimicking this data code over here, then experience 1 to 4 is, hang on, I lost it. What's going on behind me? Oh wait, darn it. There we go. Experience 1 to 4 equals experience, the full word, minus 1. Experience 4 to 7 equals 0. Boom. That is what it should be. And then we need an end. Squish this a little so I can see that. To shut off the do. Okay. There. If experience is greater than or equal to 4, then do. The first one is 3. Equals 3. The second one equals experience minus 4. And there. That is what it needs to look like. I had screwed up the ordering of these two things and swapped them in class, I believe. And that's why I had several of you making the same pattern of errors that I induced. So please accept my apologies via Candy and via an extension of your homework for one more day to sort this all out. And for those of you who did get it completed on time, you get 1 extra credit point for having done so. So, yeah. I know you guys are all grad students and you're not supposed to care about grades, but I know you still kind of do, right? So I'll just give the little carrots. I will tell you that at the end of the semester, I will give you another point of extra credit for completing evaluations. Because I'm not above bribery. I'm just not. So, yes, help yourself. Apologies via Candy. So, slopes we've got here. I've got it recording. So in case anyone's not here and they're still stuck on how to make these stupid things. Another common thing, the word experience has to be spelled correctly. So that was another common problem. SAS does not guess what you meant. It has to be perfect. It doesn't have to be case sensitive though unless you're using Stata. So any questions before I shut this down? Question? No, you have a question face. Or you're just thinking? Yeah. You're just thinking? Okay, do you need more candy? That helps with the thinking. Yeah, all right. So I will close this out then, and then we can pick up where we left off. Yes, ma'am. 3:15 to 4:15-ish. They can go like maybe 10, 15 minutes over, but not any more than that. Because I got to get out of campus before the traffic gets crazy to get to daycare. So, yes. And undergraduates have a death wish getting off campus, it seems like. They don't look where they're going, and they're like on their phones, like walking through red lights and stuff. So I just try to get out of here before the craziness happens. If you have questions, though, you can send me emails, and I can answer those afterwards. So, all right. So we started looking at a new example data set to go over regression models, general linear models that have more than one predictor at a time. So the idea of multiple concepts competing with each other for unique effects. But as always, the place that one would start, even when competing effects is the goal, is trying to figure out what the effect is per predictor in the first place. So before you control for anything else, does each predictor significantly relate to the outcome? If not, it probably doesn't need to be part of your model because it's not going to get any better, odds are, after you factor other things in. So this story comes from the chapter 2 of my book. So do you remember how I said I didn't like your book and you didn't have to read? That doesn't go for my book. So I wrote it for people who are trying to teach this stuff to themselves. That was my audience. So I hope that it is readable. It has a lot of words to go with the equations and the pictures and whatnot. So this is coming straight out of chapter 2. So we are examining an outcome of cognition. It's measured as an index of crystallized intelligence in this case. We have age as a continuous predictor or a quantitative predictor. Grip strength as another quantitative predictor. We'll have gender as a binary predictor, and dementia group, which is a 3-category predictor, in a sample of 550 people. So I think we went over the setup for this. Creating the variables that you need to go in your model is always the first step. So the quantitative predictors I have centered at values near the middle of their distributions. So there's an expression for centering. It's often referred to as grand mean centering. Have you heard that before? Maybe? Grand mean centering is probably the most common, where they literally use the grand mean as the centering constant. That's not necessary. Anything in the middle serves the goal of making the intercept a meaningful value with respect to the reference point for your model. So I just rounded them. That way, when I talk about what the intercept means, in a model with age, it's the predicted outcome for an 85-year-old. In a model with grip strength, it's the predicted outcome for someone who can squeeze 9 pounds per square inch. And that is a meaningful person within the scale of these measured variables. Dementia group, I am creating dummy codes. So I have NFC as my naming conventions here. None is group 1. Future is group 2, and 3 is current. So these are potential diagnoses of dementia that the people in the sample can have. So what does it mean that I have set group 1 equal to 0 in creating my new predictors here?
0. Is that going to be 0?
That's going to be my intercept, exactly. Might be 0. Each of the predictors then contrasts that reference group, the none group, against the future group. So that's the NF variable, that's what it's doing. And the NC variable is contrasting none with current. And foreshadowing, what will I have to do if I want to know future versus current? Estimate, linear combination of one minus the other. Yep. Making sure that I do my good due diligence in labeling everything here. For demonstration purposes, we're going to look at a model with z-scored versions of the variables, so I went ahead and made copies of those because in proc standard it overwrites the variables, and so I wanted to save the originals and have the z-score versions. Do you remember what this is for, this part right here? What's it for, Cole?
If you have missing values within the data set,
What happens to those cases?
they get kicked out.
They get kicked out. Why am I doing that?
So the same overlap.
to keep the same sample across all the models. Kicking out cases is not a good idea, like on purpose, but that's what's going to happen anyway. If they don't have an X or a Y, they can't participate in the model. And what do you have to do if you want to learn better ways of addressing missing data?
Come back next semester.
Take more classes, yeah, in general, yeah, because there are better ways. They all require untestable assumptions, though. That's the only tricky part. You really can't escape the problem of missing data. I will show you a workaround, I think, at some point this semester that I found to be useful in practice, just so that you can get a sense of what the missingness might entail for your model, but that's a story for another day, as we would say. So the code to do things in Stata looks remarkably similar. One difference is that I had to take an extra step in Stata to make squared versions of the predictors for use in getting effect sizes, whereas I didn't have to do that in SAS. And the process of generating the dummy codes, this is more lines than you need, but it makes it exactly clear what happens to each new predictor as a function of what the original group variable was. And then the analog to the if they're missing, kick them out. That's an egen. Have you seen this one before? That one? Egen is like fancy gen, as near as I can tell. It's like if it's a transformation that's not just simple arithmetic, you stick an E in front of it. I don't have a better explanation than that, but that seems to hold most of the time. Row miss is a function that computes the number of missing values across a row of data. So it does the same thing as the nmiss function. And then I have drop, which means delete, if the number missing is greater than 0. So same process. And then egen can be used to get z-scores directly within the data set. So that's one step I can save. Okay. So questions on the setup so far. These are all things that you now know how to do. Do I expect you to have this code memorized off the top of your head? No. What do I expect you to do?
Look back through our notes.
Yeah, look back through the examples, copy it into a syntax file, and hit find and replace a bunch of times to make it work for you. So think of these as like templates that you can use to do things like it in the future. If you do it enough times, you might start to memorize it, but typing from scratch is never an efficient way to go about things. So how did I know what reasonable values would be for centering my predictors, my quantitative variables? And how did I know how many groups I had in my categorical ones? Well, running descriptives. So I asked for, in SAS, proc means. So mean, standard deviation, variance, min, and max are the columns that I've requested. For my continuous outcome, my continuous predictors, and for my binary predictor, which is sort of weird since it's two groups, but not incorrect. So what does a mean of a binary variable of 0.587 mean?
There was more than one.
You can either be a 0 or a 1.
So like, there was one of them was higher proportion.
The women are the 1. Yeah, one of them is the higher proportion, the women are the 1. So what proportion of people in my sample are women?
9%.
Yeah, 0.59% and 58.7 proportion, is that how it goes? I said it backwards, you know what I mean, right? So this gives the percentage of people that's a 1. So the range, of course, 0 to 1. So age, like I said, the mean was near 85, so that's what I picked. Grip, the mean was near 9, so that's what I picked. You'll see these other numbers for standard deviation show up in things, and trying to think about what would be reasonable values for what's a high value of the predictor versus low. So those will come back up later on as well. And then gender by dementia group. Here is a cross tabulation of the frequency and the percentage in each cell. And out here on the margins, you can get the totals. So this gives you both a pairwise table as well as a marginal table, so you can know how many people are in each group. Now, foreshadowing, gender, 41% are men, 58% are women. Across dementia group, 73% are in the none group, about 20% are in the future group, and about 7% are in the current group. Now, what do you think those distributions are going to imply about our power to test for differences across those groups? What's power again? Statistical power.
It's there. They'll find it across.
For probability, you'll find it if it's there, yes. So it means not making a type 2 error. Type 2 error is missing it if it's there, right? Type 2, that's right. So what about this one right here in particular, group 3? Not a lot of group 3 people. So what does that do to my power to talk about how group 3 differs from other people? Less power, yeah. So just keep that in mind as we look at the differences in the means across these groups. The means for the bigger groups are going to be estimated more precisely, which means there's going to be more power for detecting differences across groups as well. Pictures. Pictures are always helpful to get a sense of how we might want to treat a variable in terms of including it in a model. So here's the distribution for age on the left. A little bit bimodal, but for the most part continuous. Grip strength looks fairly normal. And here's cognition. So foreshadowing. Does our outcome have to be normally distributed in order to use general linear model? Is our outcome? Correct, it does not. What does though? Residuals, what's the difference? Besides, they're in two separate pictures on either side of it. What's the difference? Right, they should be in order for the general linear model to give us accurate information because that's how it's operating, as if that were true. But what's the difference between a residual and an outcome?
Residuals observed minus action. No. Predicted minus. No.
Close?
Which one is it?
Follow that train of thought. Yep.
Observed minus predicted.
Yes, it's how far off your outcome still is from the one that's predicted by your model, right? So it's like leftover cognition. Cognition for unknown, unexplained reasons. That's supposed to be normal, and lo and behold, it is. Do you know why that is? Because I made up the data that way. But just keep in mind that if your outcome initially, making pictures like this can guide you towards which family of models might be appropriate, but it doesn't mean that it has to be normal when you look at it from scratch. It should be normal in order to use the general linear model accurately after you're done with the predictors. And so this is actually what we're going to end up with when all is said and done. Given that age and grip strength, there's no reason to think about these in sort of a linear piecewise fashion for this variable. There's no like magical age at which something is supposed to change or some magical level of grip strength. I'm going to treat them as just quantitative. However, they do have potential for nonlinear effects, right? Because it could be that is age related to cognition? The older you are, the smarter you are, or the less smart you are in this case, right? Because we're talking about cognitive decline, really, as a function of aging. Is a linear relationship reasonable? Reasonable. Is it possible that the relationship sort of attenuates at some point, slows down or speeds up? That's reasonable too. So we'll look at quadratics, and the same can be true of grip strength. Now, why would grip strength predict cognition? It's kind of a weird thing, right? Does that mean like if I go to the gym, I'm going to be smarter? It's a proxy. There's like a third variable here that's sort of overall health, and there's a big debate in the aging literature. Basically, does it all go together when it goes, right? Like if you start suffering cognitive decline, does that take your nervous system with it and you start suffering physical decline, or vice versa? So that's a common question as to whether or not cognitive abilities and physical abilities are linked together and whether their declines are linked together. So that's why grip strength is predicting cognition in this case. But the same thing may be true. There may be nonlinear relationships, so we can take a look at that. For gender and for dementia group, even though dementia group is ordinal, it seems sort of weird to fit a line through it, right? Because like 1, 2, and 3 are just labels. None versus future versus current. So we're going to treat that as a categorical predictor. And the same is going to be true for gender, although there's only 2 categories, there's only one possible difference between them. So we don't have to think too hard about what to do with So what is it called if I run a model that has, let me see here, back up to the pictures here, that has a quantitative predictor and a quantitative outcome? So we're looking for subtitles of the general linear model as the collection. Like if your advisor says, what is Lisa teaching you in that 6242? You stick this in the model, what do you call it? Starts with an R. Regression. Linear regression. You can throw that word in there if you want. That separates it from things like logistic regression, which is what it's called when you predict a binary outcome, for instance. What if I put age and grip strength together in the same model, which we're eventually going to do?
All test.
That would be used to test whether or not they work together to capture the R-square, but the technique. It's M is the right letter, though. Multiple regression or multiple linear regression. So yes. What about if we put, where is it? Gender or dementia group in the model as predictor? Then what have we done?
ANOVA,
Yeah. What does ANOVA stand for?
analysis of variance.
Correct. And if we put those two in the model and age and grip strength, and COVA, analysis of covariance. Yes, very good. See, look at all these things you can now list that you know how to do, right? You don't have to tell them it's just swapping out the type of variable. It sounds much cooler when you can list all these different things. So yes, synonyms are your friends in this case, right? So we have some basic sense of what the distributions of these variables look like, therefore how they should be treated in the model. Next thing we would want to know is what's related to what, because this is going to foreshadow what happens when we stick them all together. So I'm running proc core. These are just Pearson correlations. PW core is how you do it in Stata. And I'm only doing it for cognition, the outcome, age and grip, and gender. I'm not doing it for dementia group because the contrast for dementia group can't stand alone. Let me say this differently. These variables, DEM-NF and DEM-MT, they only have the specific interpretation of none versus future and none versus current if they work together. Otherwise, if you look at how they're coded, like DEM-NF, if I just run a correlation between that variable by itself in cognition, it's going to lump together the 1 group and the 3 group and contrast it with 2. That's not what I want. And likewise, this variable by itself as a binary variable would lump together 1 and 2 against 3. So they're not going in my correlation table. We will look at them separately in a model to see what their unique differences or their differences are before we factor in other predictors. Okay, so here's my correlation matrix. You've seen one of these before, right? We're not talking about pleases and fits anymore. That was my preschool example. This is my old people example. So let's decompose this heading right here, a little vocabulary review. This is a Pearson correlation, which means we're tracking a linear relationship between two quantitative variables for n equals 550. Probability greater than r with lines around it. Let's stop there. What does lines around r mean?
Absolute value.
Absolute value. What is r? The correlation itself, the correlation estimate. So we're saying probability greater than the absolute value of the correlation. What is the strongest a correlation can be? -1 or 1. What's the weakest it can be?
0.
Okay, great. Under HO, rho equals 0. What's HO? Yeah, what's rho? A Greek letter. It means R. It's the population R. That's the idea. Yeah, sample versus population is gone. You can just forget that. But every now and again, it shows up in the output. So the null hypothesis we're testing against is no correlation, no relationship. So the correlation values are in the first row of each of these, and I went ahead and bolded the ones that are significant so that you can show them a little bit more easily. Let's do this. Now this correlation table, so this table is what's known as a matrix. Matrices have rows and columns. This one in particular has a special name. It's a square matrix and it's symmetric. So you know what symmetric means, right? Like two sides match. So the same information is given below the diagonal here, where the diagonal is the ones, as above. So in other words, this minus 0.17 is the correlation of age with cognition. It is also the correlation of cognition with age. So half of this table is redundant, is what I'm telling you. So in practice, you will see people skip one of the halves because the other, it doesn't tell you anything new. So in this handout at the very end, where I gave you words, as always, here's my version of that table. I bolded the ones that were significant, and I didn't put anything over here, so it makes it a lot easier to see, to say for. What does the 1 on the diagonal mean? Yeah, a variable is perfectly correlated with itself. So you technically don't need to put these on here either. There's sort of a visual reference point that can be helpful. Anyone need candy? Did you get any candy, Lexi?
I did.
Okay, good.
There wasn't some more.
All right, no, this is candy break. Take a candy break while I scroll here, find where we were. Okay. Maybe I should do this every time. I once had a clinical psychologist who audited my class, and she was practicing mindfulness. And she would sit there and take one M&M at a time, and they could and just sort of pound them through class, but slowly and mindfully, so that it was like her concentration thing. So. Yeah, I don't eat M&Ms mindfully. It's like, it's not going to happen. So yes. So we have the correlation between cognition and age is negative. It is significant. It's approximately 0.2. So what does that mean? Yeah, as cognition goes up, age goes down. So let's word it as age is the predictor and cognition is the outcome. As age goes up, cognition goes down. Yes. How about cognition and grip? As as grip goes up, cognition goes up. Now these things, these correlations are both sort of estimates that we would interpret and effect sizes all in one. That's what makes them so convenient. Now this one, minus 0.2, as gender goes up, cognition goes down. How does gender go up?
The women are bringing us down, bringing the cognition down.
Not the way I would have phrased it, but correct. Yes, the women are just bringing us down. So yes, higher cognition is associated with a lower value on gender or being a man. Lower cognition is associated with being a woman. So this is, I would say, a disadvantage for women. Maybe that would be the way you could talk about it. Because yeah, you can't say as gender goes up. That makes no sense whatsoever. But I mean but if you use the same language, but in order to know what to do with this, you have to know who the 0 is and who the 1 is. Okay. So this first column here, these are giving us what are known as the bivariate relationships of each of our 3 predictors with cognition. Bivariate just means like by itself, without factoring anything else in. A synonym for that is 0 order. I don't know why. That's just a term. It doesn't make much sense to me, so that's why I don't use it. Bivariate I will use. Now these ones. What? That's like a binomial problem right there. Like, how many wrappers do you have to open before you find two of the same color? Yeah.
Lots. Okay.
Congratulations. If it were two yellows, I would say, I'm sorry. Is it just me or the yellows are like,
Okay.
like,
Well, I must be one today. Things.
oh my goodness.
You can play the lottery tonight.
I know. Right?
Yeah. Yes, you indeed. Okay, so these ones. These are the correlations among the predictors. Let's start off with a series of multiple choice. Relevant or irrelevant?
Not enough.
That's sort of a trick because it's like relevant for what? Like if my end goal is to put all these predictors into the same model predicting cognition and let them fight it out, right? For who gets credit for what? These intercorrelations among the predictors, relevant or irrelevant?
Irrelevant.
They're relevant. So if they're not correlated, such as age and gender are basically not correlated in this sample, P is 0.29. So that means 29% of the time, given this sample size, you would find a correlation more extreme than 0.05, meaning it's well within expected territory, right? Age and gender are not related. So that means that if I put them both in the same model, they'll each get to keep their own contribution. There's no overlap. So the bivariate relationship of age to cognition will be very similar to the unique relationship of age predicting cognition after controlling for gender. Now the other ones, gender and grip strength. Once again, the women are bringing us down. They can squeeze fewer pounds per square inch. Exactly. She's like, duh. So, but the size of this relationship is pretty big. So that means that if we try to pit gender and grip against each other, they're each going to get some of their contribution to the prediction knocked out by each other. And to a lesser extent, we'll see that happen with age and grip here as well. So these are things to keep in mind and to report, which is why they're...
So they are, yes, it's relevant?
It is relevant.
It is, so it is relevant. Okay.
It's going to foreshadow what's going to happen when you put the predictors together in the same model versus looking at them individually. To the extent that the predictors are correlated, their unique contributions are going to be less than their bivariate contributions. Unique means after controlling for something else. Yeah.
Can I understand it as the two things are less correlated, then their uniqueness is higher?
Their unique will be closer to their bivariate. The less related they are.
Yes, so it's like more like that separately represent what they mean.
So let me get out something here. The This Is Us chart needs to come back again for this discussion. So yeah, if two things are unrelated to each other, so if we looked at the contribution of, let's say, Kate and Jack, right? They each clean their own set of rooms. They each get as many Nintendo games if we consider them individually versus as the pair. Whereas if we compare Kate and Kevin, they each look like they're going to get 2 games by themselves, but when we put them together, each only gets 1 because of their unique room cleaning. So to the extent that there's overlap, to the extent that your predictors are correlated,
Does that mean the living room is their condition?
yeah, let's go with that. Yes, the idea of overlap. So these numbers are conveying overlap. So what would happen if this was a -1 here? What would that mean? It's perfect, right? Like if you know someone's gender, you know their grip strength. That means the other one is completely redundant, unnecessary. So it might look like gender is telling the story if you just look at a model with gender and other stuff, or it might look like grip strength is telling the story if you just look at that, but when you look at it together, they're redundant. That is a special case of correlation that's known as singularity. You don't want that. But anything less than 1, play ball. Just keep in mind that the more related your predictors are to each other, the harder it is to see what they can do uniquely. All right, so we filled out, I think, most of this section here. As always, I'm starting with an empty model. In practice, people wouldn't do this, but I'm doing it for pedagogical reasons, just to remind you what these models are giving you. The idea of the empty model is just to recreate the outcome. It's the mean of the outcome and all the variance that there is to be had. So 120 is my mean square error. That perfectly matches the variance in cognition that I got just from running the descriptives. So there it is. 120 is the variance in cognition. It is also the variance of the residual when cognition is predicted by nothing but the intercept. All right, so let's look at age. So this is review. You already know how to do this, but I think it's good to do things over and over again because that way you get better at it, right? Why not? So why did I pick age 85 as opposed to age, the original? It's the centered version. Would it have been wrong to use the original age? No, but would it be weird?
Yes.
Yes, why would it be weird?
Age 0, right?
Yeah, then I'd be predicting cognition as a newborn using a bunch of older adults. Weird.
So, quick question. So, but in your sample, aren't all of the adults age 80 or over?
Yes.
So then if you didn't center it at 85, age would go all the way down to 0?
The line would.
Oh, duh, because you have to say a number.
Yeah, it's a regression line, and like your data is all here, and the regression line just has to keep going and going and going and going over to 0. But the line does keep going.
Yeah,
Which is
that
why
makes complete sense that
yeah.
I just did not see till now.
When you get into more advanced models, in addition to predicting the fixed intercept, when you have dependency in your data and there's another level of variance to consider, you also have to predict the variance around the intercept, and that's where literally it can like not work, like the model can blow up if you try to estimate variance around a point that is so far removed from the data that it can't find it. So for now, it's never wrong, but it can be in the future, which is why I'm drilling this from the get-go. Think about your predictors and their scale before putting them in the model. Okay, so we have model results here. 1 degree of freedom in my model. That is what?
Cognition.
The cognition's the outcome. Here's my model. That, right? 1 degree of freedom, because we added beta 1. That's one more thing that we spent, so we have 1 fewer left over. So the total is 549 because they've already subtracted the intercept. We spent 1, we have 548 left over. Did adding that slope help? There are 2 different places on this output where that question is answered. Yeah? Where are they? Here's my R-square. And that. So my R-square of about 3% is significant because F said so. F is ratio over known to unknown, roughly speaking. Sums of squares is how we do it for now, but that will go away the second you leave my class. Never to be seen again. Also, the square root of F, in this case, because we only have 1 slope, T, yep, and there it is. Square root of 16 and some change is 4 and some change. So either way, the model is significant because the one slope that's in it is significant.
So I don't get to say 3% isn't big enough, it doesn't matter.
According to what is expected, it is outside of expected.
Okay.
And that is largely a function of the fact that we have 550 people. If we had like 20 people, that R-square would not be outside of expected. So the t is negative because the estimate is negative. So my intercept here, beta 0, is now 24. What is that?
Cognition.
Cognition at 85 is expected to be 24-ish, right? Do we care that that intercept is significant or not so much? Not so much, because it just means 24 is not 0. But the scale doesn't go down to 0. I mean, it goes down to 0, but that doesn't really mean anything, so we wouldn't make a big deal out of that. The slope, though, slope is negative. So the sentence that you use to describe slopes can always start out the same way. For every 1 unit difference in x, you get this much difference in y, right? So then we just plug in the words. So what's a unit of x here? A year of age, yes. So sometimes it'll be days, months, weeks. It's a year here. So for every additional year of age, y, cognition, is expected to be lower or higher?
Less.
Lower by
0.5.
0.5.
Yep. Yeah, 0.5-ish, half a point, we'll call it. Yep. Now, I didn't ask for a standardized slope to go with this because I don't have to. Putting age by itself in the model is exactly the same thing as just estimating the correlation between cognition and age. If you take that correlation and square it, do you know what you get? If you take this R and square it, you get R square. It's not a coincidence. So yeah, 0.17 and some change squared is that. So technically speaking, I did not need to run this model, but I'm just showing you, reviewing that you know how to do these things. I did need to run the next one, whether or not that linear slope of age is sufficient. I'm adding in a quadratic. In both programs, you don't have to compute the quadratic variable ahead of time. You can define it sort of on the fly. In SAS, it's an asterisk, and in Stata, it is, we want to go pound sign or hashtag, folks? Pound sign. I like how you said that indignantly, like pound sign.
Sorry.
Nope, I'm right there with you. I am not part of the Twitter, although my husband keeps telling me I need to be. He had a hashtag going for a while that was WTF Templin. So, yeah, exactly. He said a bad word. So quadratic age. Now in this case, R square looks maybe a little bigger. So after adding in quadratic age, now my model has two slopes in it, right? Now is my model significant? Still yes, but look at how much smaller my f is. It went from 16 down to 8. Like 16 divided by 2 almost. Because f is like, it's per slope to get the information, to get the known. And having something in the model that doesn't help drags down the average contribution of your slopes. So even though the model is still significant, we don't know how much of that has to do with each of the predictors, and that's why we have the results that go with each of these. So there's some new stuff on here that you haven't seen yet, because we just started talking about it. I've printed on here this new section, which shows up when you ask for effect size. SS3 stands for sums of squares that are type 3. That's almost always the kind that you want. It's the kind where it's not hierarchical, meaning that each one is fighting against each other. So let's look at this section right here. So the intercept, has the definition of the intercept changed? Expected cognition for someone who's 85. Still the case, right? What has changed is what expected is, because now it's from a bendy line, not a straight line. The slope for age before was 1/2 point. Now it's 6/10 of a point. Has the definition of what that slope means changed? It's the slope per year of age, but what does the quadratic do to it? We're people making the hand signs. Let me get out my handy dandy pointer. Remember? The slope changes?
Yes.
So this is the slope at 85 specifically. Because putting a quadratic in the model means the slope either speeds up or slows down. We have a negative linear slope at age 85. We have a positive quadratic, so they're working in opposition. So remember, there's only 4 kinds of quadratics. It takes the linear slope and makes it more positive, more negative, or less negative. Which one is this? Now this one's negative, and this one's positive.
Less negative.
This is a less negative. It's slowing it down. However, is it slowing it down significantly? No. In other words, this slope estimate of 0.02, not that different from 0. Well within expected territory, where the range of expected is given by the standard error. So we don't need this. It's dragging us down. So each of these slopes are given in unstandardized estimates, right? They're in units of x and units of y. Effect sizes to go with it. I could ask for standardized slopes, but that actually gets really tricky when you have multiplicative variables like this. Quadratics are interaction terms more generally, because the order of operations for the standardization matters. If you try to create a new variable and standardize it, you get a different result than if you try to standardize based on this variable. There's an order of operations problem that makes the results non-comparable. But what you can do is right here. Your new best friend, semi-partial eta square. I couldn't make this stuff up, sorry. Eta is R for all intents and purposes. When you see eta, it's in the R metric. It's more of a generic effect size. Eta square is then in an R squared metric, so it goes from 0 to 1. What this is the unique contribution to the R square for each of these predictors. Unique. Now, do you think that age and age squared are correlated? Yeah. So figuring out what's unique is a little tricky, but most of it, so 2% of the variance that's explained came from linear age, and only a tiny little bit came from quadratic age. 5, I'm going to go with 10 thousandths. Is that right, math people? Yeah, I'll stick with a little bit. Not very much. So putting it together, this slope is not significant. Its effect size is tiny. that pretty much indicates we don't need it. So that there's no evidence here that adding a quadratic effective age helps my prediction of cognition. So in this case, could I have gotten this R square just by looking at the correlation table here? Mm-mm. Because it's the R square is a combination of things that's factoring in their relatedness, what they have in common. So the only way to figure out if age and age squared are both necessary is to run a model like this. Omega square, by the way, this one, that one is sort of like the adjusted R square. I showed that to you once and said I've never been asked for it, but I included it just in case reviewer 3 wants it. This one adjusts for sample size. So you can choose to report whichever one you want. Just be clear as to which one it is. This one, the semi-partial eta square, is the one that maps directly onto this R square, which is what's given by default. So that's the one I'm going with for today. So last question here then. Do we know if the R squared changed significantly relative to the linear age model? Is there anything on this output that tells us that? What do you think?
Semi-partial eta square.
Well, this gives us an effect size, but I'm using the magic word significant. Did the change in R square that is due to this, as well as their common variance, is that change in R square significant? Is there anything on this output that tells me that? Or do I need to ask for that separately? Change in R square, yeah. So it was, the linear age model's R square was 0.029054, and now it is 0.029590. It is from age squared. That's right. That line right there is the only reason the models differ. If that new reason is not significant, it's not a better model, meaning the change in R square is not significant. When you only add one thing, the test of that one new thing is the same as the test as the change in R square. When you add more than one new thing, it's not the same. I'll teach you how to handle that problem next. So I saved the results of this model in order to do math on them. Given t, tell you where I got this from. Here's some formulae. Given t, you can compute an R and you can compute a D. D is standardized mean difference. That's more relevant when you're talking about categorical predictors, whereas R is supposed to be analogous to Pearson's correlation, but it's the unique version. So I am saving those estimates, building those new quantities from the estimates, and printing them. So when all is said and done, I'll have a table that's comparing all the different ways we can talk about effect size, and you can see that they're not exactly going to be the same. Okay. All right, questions so far? All right, grip strength. Looking at each of these individually to see what matters. Grip strength results in a significant model. Square root of my F for the model is my T for grip strength. The standardized slope for that grip strength slope would be the correlation between grip and cognition. Intercept is 24 according to this model for what kind of person? Not 85-year-old. 85 is gone. Yeah, it would be if they're both in there. But just now, for someone who can squeeze 9 pounds. For every unit X This is what happens to y. Okay, so for every, what's a unit here? Every pound per square inch more that you can squeeze, your cognition goes, or is higher, however you want to phrase that, by 0.9. Yeah. See, there's a reason that I can write results sections with drop-down windows that cover every scenario, because this is totally algorithmic. Like the way that people talk about these things, technical writing is very, very different than any kind of writing that you've probably done before. You want to be boring and formulaic. Synonyms are the devil. Seriously. The more boring, the easier it will be to follow. And so honestly, this is the language that people would use, and it's highly standardized so that it's easy to follow. Grip strength quadratic. Same question, do we need to make the line a little bendy? 2 slopes now. My F is smaller as a result of it trying to figure out information for each. R square is increased by a little tiny bit. Semi-partial eta square, the linear coefficient for grip, the linear slope is responsible for 5.8% of my R square. The quadratic is a tiny little bit here. Same sort of conclusion. However, which pattern is this? So the linear slope for grip is at 9 pounds. It's positive. What happens to it as grip increases? These are both positive numbers. More positive. By how much? And don't say 0.01. Non-significant, but by how much according to the coefficient? What's the rule? Times 2. Yes. So if I said this is 0.016 would be like 0.320, I would say the linear slope for grip strength becomes more positive by 0.320 per pound of grip strength. Twice the quadratic, that's the rule. Because the quadratic is half the rate of acceleration. And last but not least, do we know, just from this, if the R square changed relative to the typo here, linear grip model? Yes, we do know. It did not. So we don't need it. Here's some effect sizes from that result.
Right there, we looked at the P. Right.
Yep. If you add one thing to the model, and that one thing is not significant, you know the R squared change that resulted from that one thing is also not significant. It's a 1-to-1 correspondence. Now gender. Looking at that all by itself, reminding you how to get linear combinations so that you can get predicted outcomes for any group. So men are the 0, women are the 1. So what you get from this model will be the intercept, which is always for the group coded 0. So that is for dudes here, right? Beta 1 is what? What does beta 1 represent? It's the slope for gender. Now, how do we think about slope when we're talking about groups? It's binary, yeah. So here's the mean for men and the mean for women, right? Beta 1 gives us what? Difference. Yes, that's what I'm looking for. This is a very common source of confusion to think that it gives you what the mean is for women. It does not. It gives you what the difference is for women. So beta 0 does give you the mean for men because the intercept is the expected outcome when x is 0. Beta 1 gives you the difference for women. So to get what it is for women, you got to add them together. And that's the linear combination that you would have to ask for if you wanted that information. So I am trying to help map the logic onto the code with comments here. So I wrote out all three things that you would want to know via estimate statements and via lincom statements and stata, but only one of these is given to me, is not already given to me in the model. So beta 0 is the intercept. Men versus women is beta 1. So it's only the middle one, beta 0 plus beta 1, that I have to ask for specifically as a linear combination. And could I just do the math and be like, well, beta 0 is, let me go down here and find out. Beta 0 is 27 and gender is -5, so it's going to be about 22.
You don't know the P and
Yeah, I don't know the standard error. I don't have any of that. So you know what using your calculator is good for? Checking that you wrote your estimate correctly. Right? Like if you get your calculator out and you're like, it should be 22, and you get a number that's not 22, something happened. Do we need some more candy? Everyone's like flagging. Maybe now we're coming down on the sugar rush, right? It's like, yeah, see? Aren't you glad this isn't a 3-hour class? Just saying. It's challenging to maintain high energy and focus for an extended period of time. Yes. So yes, the intercept, that's what cognition is predicted to be for men. It is predicted to be lower by 5 for women, resulting in predicted cognition for women of 22. And the effect size that goes with that gender difference was already given to us right here. Okay. Last single model, and then we can put it together, likely next time. Our 3-group variable. So this is the one that we don't have correlations for, because the definition of these dummy codes is different when you put them together in the same model than when they're looked at individually. So here, beta 0, always the expected outcome for the 0 group. Given my coding, none is 0, future is 1, none is 0, current is 1. Who is beta 0 for? And feel free to read from behind me.
No.
The none group. What does beta 1 tell me? Difference. It's a slope. Between none and future. More specifically, it is how future differs from none. Future is the 1. They get the coefficient. Likewise, beta 2, how current differs from none. So in terms of my 3 possible differences among my 3 groups, 2 of them are already model parameters. The third is the linear combination. Beta 2 minus beta 1 gives me how future and current differ from each other. Likewise, the none mean is the one fixed effect that is given directly by the model. To get the predicted means for the other groups, those require linear combinations. To make it optimally clear, though, I wrote out all 6 for each, just so you could see the logic of what goes in and what goes out. One thing to keep in mind, whenever you are requesting differences, so slopes or differences broadly construed, intercept does not go there. It drops. The intercept contributes to each group mean, but it cancels in thinking about how one mean differs from the other. The only time that you need intercept is when what you're trying to create is a predicted outcome for a specific type of person. In this case, the mean for cognition for the none group, or the future group, or the current group. And once again, I'm saving the results of the model to compute effect sizes with, although I'm saving more specifically this set, because they're the ones that have the complete listing of all the differences that I would want. One thing I think I forgot to mention explicitly for Stata folks, your semi-partial R-squares do not come out of regress. You have to do a separate command called pcore. Not to be confused with pwcore or core. pcore. Yes. I had to find that out. I had no idea about that. All right. So this is an example now of not a one-to-one mapping of the model to the parameters. These two slopes work together to distinguish the three groups. So in terms of concept, my model has only one predictor, right? Its dementia group as like one idea, but it takes two slopes, I need some candy, two slopes to differentiate three groups. See, that's where I was going. Put group and slope together. So it takes two slopes to differentiate three groups. That's why my model has my two slopes in it. If I had four groups, how many slopes would I need? 3, yes. So these two slopes work together to get my R-square of about 17%. That's pretty big. The model is significant. So R-square, we're talking about that so far as proportion, reduction, and variance, right? 17% of all the reasons why cognition differs across people in my sample is because of their dementia standing. But it is also the square of the correlation between what and what. Predicted and observed, right? Y hat and Y. So it takes two slopes to get a predicted Y hat for each person, because I have to know what their standing is on each of those dummy variables. So here, I get a semi-partial eta square for the none versus future. So 4% out of that 17, 4 came from the difference between none and future, and 15 came from none and current. If you add those up, it's actually more than the R-square, which is interesting in this case, but it has to do with the fact that they're not independent contrasts. They work together. Here's my model results. 27 is predicted cognition for what kind of person? The none group. Relative to them, what happens in the future group? Lower by 5-ish, right? Relative to my none group of 27, what happens in my current group? Much lower by 16. And if I take the difference between these slopes, minus 16 versus minus 5, that is the mean difference of future versus current. That's my linear combination. So all three groups differ significantly. I've got effect sizes for each of those contrasts. It looks like the biggest difference, unsurprisingly, is none versus current, and then future versus current, and then none versus future. So these are means per group in my analysis of variance. Once we put other predictors in the model, these means take a special name. They're called adjusted, because what they would be depends on what the values of the other predictors would be as well. Okay. I need to change this. This is another copy-paste error. So I have a heading here with all predictors of cognition, and yet I only have a couple things in here. So let's fix it, shall we? Age minus 85 should be there. Beta 2 is grip sub I minus 9. Beta 3 is gender, which I had said sex MW underscore I. And I don't need a 9 on that. Do you remember why some of these things get I's and some of them don't? Which ones are constants? The one without the I's, yes. So all the things that are variables here get I's. Dem, F, I. And I will post a new version of this with this fixed after class, of course. There. That's better. Ta-da! So all 5 of these things are going in. What is this called again? I'll call it ANCOVA or multiple regression, your choice. So what's going to change? Are the fixed effects that we got in the individual models with each of these predictors going to be the same as the ones we're going to get below? Mm-mm. The ones that we get below are their unique effects, the ones that factor in the covariance between them, or what is referred to as collinearity in this context. I'm asking for a bunch of extra stuff here, which is something that I don't think you've seen yet, so we'll have to talk about that next time, as well as adjusted mean differences for the dementia groups. And stata code looks very much the same. I had a question once about this here. So in SAS, it's like model y equals the x's. It follows the structure of the equation. Whereas in stata, you just have to know that the first thing listed is the y and everything that follows is x. You just have to know that. So, all right. Questions? Well, then we will pick this up next week. I will have a formative assessment for you to do before the next class. Same story as usual, 2 points graded on effort, and we will go over it on Tuesday. So I will let you know as soon as that is ready. Let me know if you need any further help with your homework or questions otherwise. Grab some candy for the trip home, and I will see you next week. Unless you want to come to office hours, in which case I'll see you at 3:15.